Hey, science time. Today we're talking about light again. Light, and we already talked about most of this, so this will be pretty, I would say, brief. We're going to talk about two things that we didn't have a chance to talk about last time, but we're going to call this light interactions part 2. This is the Roman numeral 2, not the Arabic numeral 11. Light interactions part 2. So we had talked about what light is, if you recall. Remember talking about that? We talked about the light is a transverse electromagnetic wave, and that there's more to light than just the light we see. With that little portion of the electromagnetic spectrum we call, what we normally call light, visible light, is just very, very small. And then with a longer wavelength than visible light, we had infrared, microwaves, and radio waves. You remember this? And then with a shorter wavelength than visible light, we had ultraviolet, X-rays, and gamma rays. Yes, all this is ringing a bell. And then within the spectrum, as your bell work has, within the spectrum of colored visible light that we can see, the longest wavelength was, what color?
Purple.
No, red. The shortest wavelength was purple. So that rainbow, what we see as different colors, is actually different frequencies of light. And remember, different frequencies of light are also different wavelengths of light. So all that should be reviewed. And then we also talked about the idea of reflection, transmission, and absorption, but only briefly. So let's talk about those again real quick. Reflection, transmission, and absorption. Would someone volunteer to run into the lab and get me one of the pretty nice LED flashlights and a mirror and the colored acetate or the colored paddles? Either one is fine. I don't care who it is, just go do it. I should have grabbed those ahead of time, but I didn't even think about it until just now. So what does it mean for a wave to reflect? Let's draw a little diagram of a wave reflecting. Someone said last time, a mirror. Are mirrors the only thing that reflect? No. Look at, why is no one wearing a red shirt? I like to use the red shirt. Oh! Look at Tegan's shirt that is underneath her other shirt. Oh, look at Sage's shirt instead. Don't look at Tegan anymore. Could you take off your jacket, please, so we can all look at your shirt? Look at Sage's red shirt. Is it red light?
No. Yes.
Let me phrase it differently, because you could answer, not only could you, but you did answer two different ways, and it's a yes or no question. So, is her shirt emitting red light? Do you know what I mean by the word emitting? Is it producing red light? No, it is not producing red light. What is it doing? Why do we see it as red? Right, it's reflecting the red part of the white light. Remember, white light is all the different colors of light squished together. And so the white light coming from, in this case, mostly the LEDs, probably a little bit of sunlight, both of which are white. The white light that's coming from those is crashing into, well, that's a little bit violent, is interacting with Sage's red shirt, and her shirt is absorbing all the parts of the white light. Red, red, orange, orange, yellow, green, blue, purple, 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 purple. It's absorbing all those parts except the red, and the red is being reflected. So reflection is not just about an image reflection. A mirror reflects an image, but all surfaces, most surfaces, actually all surfaces reflect. Oh, could you get the red, green, and blue little paddles? Thank you. I'll take the purple one too. And then this is not the good flashlight, dog. Could you get one of those good LED flashlights? Does anyone know where they actually are? Just go help her, Miranda. I'm sorry, Josie. If I had realized this would be difficult, I would have done it beforehand. Also, if I had realized I was going to do it, I would have done it beforehand. Let's actually turn off the light. I'll do my spooky face too. And shut that door too, because we're going to want some light for this. Sage, would you mind being in the video for a demonstration? You can say no if you don't want to. You have signed a release waiver, though. That doesn't mean you have to be in the video, but it means that the video can be published with you in it. Shut the light off and shut that door. Yeah, shut the blinds too. Woo, it's spooky. You see how spooky it is? Once upon a time, all the 8th graders did not study very well for their Module D Unit 2 test, and so they all got a B. Oh no, and that better not happen again with the Module L Unit 1 test. Okay. Sage, come here. Look, I have this purple light on. Actually, it turned itself on. And would you hop up, Cody, and do the white light, please? Come over here, Sage. Yeah, white light. Turn the white light on. turn the white light on, please. Also shut the lab door. So in this case, could you back right up against the wall? I could have actually, now that I'm realizing, I could have just drawn a red shirt on the board, and it would serve the exact same purpose as you being here. But I'm happy for you to be here, Sage. This is my boy Sage. And right now with the white light happening, the white light is coming in. Let's draw, even though she's right here, let's draw a little diagram. This is Sage with her red shirt on. And the white light, which I'm going to indicate with black, is coming from the lights. There's the lights. The white light, which is composed of what kinds of light? All kinds. The white light is coming toward the shirt, and the shirt is absorbing, and I'm going to indicate that with little dots on here, but the shirt is absorbing. Let's go through the spectrum, the rainbow. Is it absorbing the red light? No. The red light is being reflected back into your eye. You have beautiful blue eyes. Not you, Sage. Do you have blue eyes? No. Okay, you as a group of 8th graders have beautiful blue eyes, and so that's what I'm going to draw here. But the red light is going into your little eye, right? It's reflecting into your eye. Is it only reflecting into your eye like a laser beam? No, it's being spread out everywhere. Someone else with beautiful blue eyes is also seeing the red light. But the red light is being scattered and reflected by the shirt. Next, orange. What's happening to the orange light as it interacts with the shirt?
It absorbs it.
It's being absorbed. So it's just, that was orange. What's happening to the yellow light?
Being absorbed.
Being absorbed. What's happening to the green light?
Being absorbed.
What's happening to the blue light?
Being absorbed.
What's happening to the purple light?
Being absorbed.
All the other colors of light are being absorbed. Hey, what's happening to the infrared light?
It is not being absorbed.
We don't know. Why do we not know?
Because we don't.
We can't see it. We can't see it. Probably some of it's being reflected. Why would I think that on her red shirt some of the infrared light is being reflected? Because, yeah, right next to red on the electromagnetic spectrum is infrared. Okay, so here's Sage's red shirt. Here's Sage's red shirt. Now, would you please turn off the white light? Now we have, don't look at this. Do not look into this, Sage. Close your eyes. Now we have this, let me switch it to blue. Don't look into the light, Sage.
Oh, we're not supposed to be looking.
You are not supposed. Okay, so now we have blue. Oh man, what color does Sage's shirt look like? No, it doesn't. You know it's red because you just saw it be red. It does not look purple. There's still a little bit of white light in the room, but if there wasn't white light, you would see.
Blue.
No, it doesn't. It does not. It should. I wish she has blue jeans on. I wish you hadn't seen Sage's shirt that you know it's red. Try to shake the color red out of your eyes. But it does look. You could say it looks like dark purple. And these do have a little bit of white light too. They're not pure blue light. But yeah, you don't look in it, remember? It should. If this was pure blue light, and actually you can tell really well on video, it looks black. Because what before was reflecting when there was white light? Remember, the white light is all of them.
Red.
Red was reflecting. But the blue light, and this is blue plus white, but if this was just blue light, what would reflect from our shirt? No. No. None. Yeah, because there's no red light in the blue light. So none of them would reflect. They'd all be absorbed, and all here being the blue wavelengths, would be absorbed, and her shirt would look like it, black. Because if something absorbs all the colors of light and reflects none of them, that looks to us to be black. That is, it reflects all of them equally. You can go sit down. Turn the shirt back on. Turn the light back on. Who's wearing a black shirt? Cody, come up here. Off, please. Do you want to come up here? Okay. This is my boy Cody. What color is his shirt? Is it reflecting light?
No.
Try again.
Yes.
How do you know it's reflecting light? No, okay, because I told you it was. Because you can see it. If it was absorbing all light, like this pigment you might have seen on TikTok like I did called Vanta Black, which absorbs 99.999 some % of the light, you just cannot see it. Like if he was wearing a shirt that was pigmented with Vanta Black, you wouldn't be able to tell there were buttons. Like you wouldn't see anything on it. So the fact that we can see it at all means it's reflecting some light. But why do we see it as black? Well, it's reflecting all the colors equally back. Let's draw his little black shirt here. Yeah, it's reflecting all of them back, but less than, for instance, Peyton, do you want to be on the video? No. Peyton is, for the record, I knew she was going to say no. Peyton is, for the record, wearing a white shirt. So how come her shirt looks white when it reflects all of them back, and Cody's shirt looks black when it reflects all of them back? Tommy don't know.
Different combination.
No, not a different combination, but a different No, it's the same spectrum, all of the colors of light. It's just that his is absorbing most of them. And so only a very, very little bit is getting into your now black eyes. And hers is reflecting more. It's a matter of quantity. So the black shirt is still reflecting all the different colors equally, just not very much. And the white shirt is reflecting all the different colors equally, but more. Does that make sense? And this is all reflection. Thank you. Oh, wait, hold on, one last thing. Turn that light off. No, Cody can't do it because Cody's still here. Turn that light off and let me turn this one. Don't look at this, Cody. Oh, there we go. Look at, what color does it look like?
Black.
Still black. Still black. So even though, because now the only light that's available is blue, and it's still absorbing that, so it still looks black. What color do his pants look?
Black.
Black, yeah, or well, blue, because it's blue light reflecting blue, but all of it kind of looks blue. Thank you, Cody. What color does his little white face look? Blue, because his white face now, what we normally see as white, and it's not perfectly white. Don't trick yourselves into thinking your skin color is actually white. What normally we see as like orangish pink of Cody's face is reflecting more orangish pink light than it is the other colors. But when the blue light is on, it's reflecting just blue light, and so we see his face as blue. We could use my face for that too, because look at me. Don't look at it though. Blue. And my shirt, which was blue before, is still blue. And my collar, which was white before, is now blue because only kind of light available is blue. Does that make sense? Turn the light back on. Okay. So actually, we've kind of talked about both reflection and absorption, and I can't see anything anymore. You go away. You're really hurting me. We kind of talked about both the reflection and absorption. So reflection is when the light bounces back, and absorption is when the light is absorbed into the material. So what is transmission then? Yeah. So if reflection is like this, and absorption is like this, what is transmission like?
It goes all the way through.
Yeah, it's going through it.
So like
It's transmitting the light. Do you transmit light through your body?
Yep.
No. Jellyfish do. This is transmitting light. Look, you can see me through it. There are different kinds of transmission. We talk in transmission about transparent, translucent, and opaque. You tricked me, Garrett. Transparent means an image can be seen. It transmits an image. Translucent means only the light can be detected but no image, and opaque means no transmission. Is this transparent or translucent?
Transparent.
It's transparent. How many fingers am I holding up? Two. It's How many fingers am I holding up through it? Two. You can see because it's transparent. I don't have one. Where'd my little... I saw someone brought me an LED light.
Yeah, it's on your whiteboard.
Oh, I put it over here like I wasn't supposed to. Let me get one other thing out here. Look at him. Transparent, translucent, or opaque? It's translucent, because look, you can see the light, can't you?
Yep.
Yeah, you can see the light. But can you see how many fingers I'm holding up?
No.
How many fingers am I holding up?
1.
So you can't see the image. So this one, the light transmits through, and an image can be seen. This one, that's transparent. This one that's translucent, the light does pass through, but an image cannot be seen. And then this one, can you see the light? Is the light on or off?
Opaque.
It's opaque. The light is not transmitted at all. Okay. I think that's good. Oh, let's talk about refraction. Let's talk. That's great. That's right.
That's when you stick a straw in the
It only has to do with straws, right? Refraction is when light changes medium, it bends. Refraction. Let's just knock all the markers off. Refraction is the bending of light due to change in medium. But wait a minute, I thought light did not need a medium to travel through. That's right, light does not need a medium to travel through. Remember, sound needs a medium. Light does not need a medium. But can light travel through a medium? Yeah, it doesn't need a medium, but it can travel through a medium. How do you know? Well, What's the light traveling through right now?
Medium. Air.
Air. Yeah, it's traveling through the air. The air is not a vacuum. The air is, I'm trying to get right in the camera. I'm going to shine it right in Miranda. The air is a medium. The light can travel through a medium. What if, that's not really going to work very good. I need a glass of water. Well, you did it in your lab, so you've already seen this, but when you put the straw in the glass of water, the straw appears to be bent. Not because the straw has actually been bent, but because the speed of light is different in the water than it is in the air. So it looks like this. The straw, which has not been broken, looks like this because the light is traveling at a different speed through the liquid water than it does through the gaseous air. The same thing happens when, or a similar thing happens when planet Earth, which is sitting here in outer space, surrounded by a beautiful atmosphere that we love, when the light is coming from the sun, you know how brown light comes from the sun, the light is bent. And so even if you're here, this is Tommy Tiger and she's here, even if you're here, you can still see the sun after it has officially set. So here's the sun. The sun's actually for you below the horizon, but due to the refraction of the Earth's atmosphere, you can still see it. And even after the image of the sun has set below the horizon, you can still see the light from the sun because the light is refracting and scattering, or sorry, the air is refracting and scattering that light. That's called refraction. And then last we have the idea of color addition. There are two ways that color kind of work in our understanding. There's pigment mixing, which is color by subtraction, and then there is light mixing, which is color by addition. So if I mix together, you know this from art class, but if I mix together red and blue, I should get, kind of did. Doesn't work great with dry erase marker, but I kind of got purple there. Let's think about what colors of light, I want my black, where did my black marker go? Let's think about what colors of light were in the blue. So how does the blue light that is this pigment work? It's absorbing white, or it's taking white light from the light. It's not taking it, but the white light is coming into the blue. And what's reflecting back? Blue. So we started with red, orange, orange, yellow, green, blue, purple, 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 purple. And which light's left that reflects? Blue. So all these are absorbed. Oops, not you. All these are absorbed. What about for the red? Well, we had red, orange, orange, yellow, green, blue, purple, 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 purple. All of them are absorbed except red. So that's color change, I have purple now, by subtraction. So now there's less red in this little one in the middle. There's less red because the red is absorbed by the blue, like half red. There's no orange, no yellow, no green, half blue, and no purple, right? And so I'm left with just like a little bit of light that is a combination of red and blue, which shows up as purple. This is for pigments, and it's called color change by subtraction. It's subtracting light. This is always going to be what we would say darker than the two it started out with, because the pigment works by subtracting light. It's absorbing new colors of light. Whereas, if I have, which I do somewhere, I have these color paddles, it's also going to be dimmer, but we say this is a color change by addition. Hey. So this is white, blue. If I put the green over it, it gets very, very dim. These are not how I want them to be. It should be cyan, though. So now instead of, if we mix blue and green together in pigments, we would get what we call blue-green, and it would be darker than both. The reason this isn't working super well is that you're supposed to do this with different colors of actual lights, like different things that are emitting light, not blocking the light out, so it's not going to work super great. But this will make the color cyan, and then if we add red, it should make white light again. Where, can you see it? I mean, it's just doing its best. You can see that the color has changed, and it's supposed to be white again. But this is called color change by addition, because we're adding new colors of light. To be clear, what you're supposed to do is you're supposed to have like a red light, like not something blocking it that makes it red, but a red light like a laser or an LED or something, and a blue light and a green light. Kind of like these LEDs. There's not a green one in here. Why would there not be a green LED in here? We talked about this last time. Why does this grow light not have green LEDs? Because the plants don't absorb green light. So this doesn't need to have green LEDs in it. But if it did, and I switched it to a different color, so that's blue. This one is the magenta light. And then this one that shows up as purple is actually the magenta and the blue together. And you can see in this case, because it's the lights themselves, this is not dimmer. This little splotch on the wall is not dimmer than it was when it was blue or magenta. It's just a combination of them. If there was green, now it would look white, because the green light would be added to that and it would make white. But this is color change by addition. So we start out, instead of with white light that we're blocking colors of, we start out with different colors of light. So we start with red light, and we add green to it, and then we add blue to it. So if we add red and green, we get, can anyone guess?
Red, green.
Yellow. If we add green and blue, we get, I'm going to have to find this color. Green, blue, which is called
Blue-green.
cyan. And if we add cyan and yellow, or if we add the first three all together, we get, no, white. It's kind of like the reverse, because here we started out with white light, and we started out with white light, which was red, red, orange, orange, yellow, green, blue. Do you see how that's the same thing as white? Right? So we start out with white light, and we're taking colors away from the white light to make other colors. In this case, we start with red, green, and blue light, and we add them together to end up with white light. Do you have questions on any of this? Me neither.